Strong acids and strong bases are completely ionized in solution. There are 6 strong acids: HCl, HBr, HI, HClO4, HNO3, and H2SO4. If it's not one of these 6 strong acids, it is a weak acid. You have to know these 6 strong acids. Now the strong bases all have hydroxide. So I'm not going to try to trick you with the strong base. If it has hydroxide, it is a strong base. Here's what it means to completely ionize in solution. If I have HCl, which is a strong acid, I put it in water, it completely breaks apart into H plus and Cl minus. It's a complete dissociation. So 100% ions in solution. Same thing with a base. If I have NaOH, which is a strong base, and I put it in water, it completely ionizes in water, which means I have 100% ions, 100% Na plus and OH minus. So let's look at an example of a strong acid problem here. We have an HCl solution, and I want to calculate hydronium, chloride, and hydroxide ion concentrations. Well, HCl is a strong acid, so when I put it in water, it breaks apart into H plus and Cl minus. Concentration of HCl is 0.05. Since it's a strong acid and it completely dissociates, the concentration of H plus is 0.05, and the concentration of chloride is 0.05. So the concentration of H plus, which is H3O, is 0.05. Chloride is 0.05. So I found those two. Now I need to find OH. Well, I know if I take H3O times OH, that's equal to 1 times 10 to the negative 14th. That's a constant. So I plug in my H3O, which is 0.05, and that will allow me to find the hydroxide. So hydroxide comes out to 2 times 10 to the negative 13th molar. Very small concentration of hydroxide, and I would expect that because this is an acidic solution. This is only coming from the dissociation of water. So that's where the hydroxide actually comes from, the dissociation of water, and it's very small compared to the hydronium ion concentration. And we could go back to this equation. The dissociation of water produces H3O and OH minus. Well, according to Le Chatelier's principle, if I increase the amount of H3O, that's going to shift equilibrium to the left, and that's going to dramatically decrease the amount of hydroxide. So the hydronium derived from water is equal to 2 times 10 to the negative 13th. This is negligible compared to the 0.05 that I get from the acid dissociation. Here are some other equations. We're going to use the pH scale. It's a convenient scale that will allow us to tell whether a solution is acidic, basic, or neutral. pH is negative log of H3O plus. This is one of the 4 main equations that we're going to use. There's also a pOH scale, which is negative log of OH minus. Then we have 14 equals pH plus pOH. And then we have the equation that I just used, H3O times OH is equal to 1 times 10 to the negative 14th. So these are the 4 equations that we will use quite frequently in going from H plus to OH minus to pH to pOH. So let's look at an example here with a nitric acid solution. This is a strong acid. So if we have a strong acid, I know the concentration of H3O is the same as the acid. So H3O is 0.04 molar. So there's one of the quantities that I needed to find. To find OH, I can take 10 to the negative 14th divided by H3O, which is 0.04. So the OH concentration, it's going to be very small 2.5, 10 to the negative 13th molar. We would expect that to be small though because this is an acidic solution. Now to find the pH, pH is equal to negative log of H3O, which is negative log of 0.04. And if you find this function on your calculator, so that you can get the same answer that I'm getting, you'll get a pH of 1.4, which tells me that's very acidic because the pH is below 7. And then finally, to get the pOH, I know the pH plus the pOH equals 14. So I have 1.4 plus pOH equals 14. So pOH, subtract, you get 12.60 is the pOH. So there are the 4 quantities for the nitric acid solution. In this example, what are the hydronium ion and hydroxide ion concentrations if we have a pH of 4.4? Well, pH equals negative log of H3O plus, and that equals 4.4. I'm going to bring the negative sign to the other side. So log of H3O equals negative 4.4. Now to get rid of log, we're going to take the anti-log, which on your calculator is the button right above the log key. It's the function right above the log key. It's 10 to the x. So to get the concentration of H3O, I'm going to take the anti-log, which is 10 to the negative 4.40, and you should get an H3O concentration of 4 times 10 to the negative 5. So make sure you can get that on your calculator. There's the hydronium ion. To get the hydroxide ion, I'm going to take 10 to the negative 14th divided by my hydronium. And so hydroxide comes out to be 2.5 times 10 to the negative 10th. So again, just make sure you can get those answers on your calculator using the log functions. All right, so here's a little bit about the pH scale and your possible ranges for hydronium and hydroxide. You'll notice hydronium can go anywhere from 1 down to 1 times 10 to the negative 14th. I want to point out the pH scale right here. Now the pH scale goes from 0 to 14. And this is the best way to tell whether a solution is acidic, basic, or neutral. If the pH is from 0 to 7, it's acidic. If the pH is from 7 to 14, it is basic. Right at 7, it's neutral. There's also a pOH scale, but the best way to tell whether a solution is acidic or basic, go to the pH.